Welcome to the webinar on Challenging Micrograph Analysis, the latest in computer vision. My name is John Sosa, and I'm the CEO and co-founder here at MIPAR Image Analysis Software. Users come to MIPAR looking for practical solutions to their real image analysis problems, primarily when those problems have proved too difficult for other solutions in the past. Today we'll be taking a close look at three cases that represent many of the extreme challenges that researchers face when trying to quantify micrographs. Each of these cases were chosen as they demonstrate common challenges that are not only seen in the applications you'll see presented today, but in many others across many fields of study. MIPAR has been used in applications including material science, life science, agriculture, and even drone imaging. Today's applications will be in the material science space, and each of them will have relied on SEM imaging. So let's get started. Here are the three applications we'll cover today. As I mentioned, not only are they challenging in and of themselves and represent common applications, but each of these cases offer a series of challenges that are seen in many other problems as well. In the grains with twins case, we have to tackle the challenge of identifying grain boundaries, which are often only revealed by the local variation in complex pattern differences. We have to teach the computer how to recognize these grain shapes while ignoring the very abrupt, in many cases more obvious, twin boundaries. In the case of this loose particle analysis, we have to deal with features that sit on top of one another. We have to deal with ambiguous boundaries between features where some objects need to be separated from others, but others need to be kept together, as well as dealing with often very low and varying contrast within the features of interest. And in the nanofiber analysis case, we have to deal with pretty much everything we saw in the loose particle case, but to an even greater extent. Next to no contrast between the features in the background, and an extremely chaotic and overlapping network of features that makes it very difficult to isolate individual ones such that they can be measured. So in each of these cases, we'll cover the key challenges that the community has struggled with for some time, and we'll demonstrate, using MIPAR software, how a solution was developed in each of these cases. You'll then also see the all-important resulting measurements that were made possible because of an accurate feature detection. So let's get started with the grains with twins. In this case, here we have an SEM image, in fact, a series of SEM images, which reveal a grain structure. As I've mentioned, the grain structure is a heavily twinned one. Each of these strips and very linear features represent a twin boundary within the material's grain structure. These represent slight variations in crystal orientation within a single grain. In order for software to accurately quantify the grain size from an image like this, the software must accurately identify only grain boundaries and not falsely identify twin boundaries as grain boundaries. And as I've mentioned, this is especially challenging since the twin boundaries are often more obvious than the grain boundaries. In some cases, twins even occupy nearly an entire half of its parent grain, making them especially difficult to ignore. So for these reasons, many researchers have resorted to using EBSD, or electron backscatter diffraction, in order to have a shot at automatically identifying the grains and measuring their size. For those of you involved with EBSD, you'll know it can be an arduous technique that involves tedious sample preparation, lengthy imaging times, and expensive imaging equipment. So it's no wonder that researchers have looked to replace EBSD imaging with traditional SEM imaging, which can collect images orders of magnitude more quickly and still provide quality information to measure grain size with, provided that the boundaries can be identified automatically without the twins. Unfortunately, this has proven an impossible task to automate, and folks have had to resort to manually tracing grain boundaries or drawing manual intercepts through the structure in order to quantify the grains. They're well aware that this manual process is quite tedious and expensive, but in many cases it's less expensive than EBSD imaging, despite not being fully automated. Today I am pleased to share with you a breakthrough result, which is the first of its kind in this field. Using MIPAR software, we have been able to devise an algorithm which has been proven successful at automatically detecting grain boundaries, even in a heavily twinned material such as this one. So let's move into a live demo of this solution in action, take a look at how it works, and the types of measurements that it enables. Here we are in MIPAR's image processor. It's where individual images are analyzed, and it's even where these algorithms, or recipes as we call them, are created from the ground up. So to begin, let's open up one of the twins images. Opening it in MIPAR is trivial. Simply drag it in from the File Explorer and open it up. Now what we'll first take a look at is an algorithm that not too long ago was the state of the art. To load a recipe in MIPAR, either drag it in, just like you did the image, or you can choose it from your Recents menu. So here we see an algorithm or a recipe that was put together using conventional image analysis approaches. A combination of things like edge detection, noise filtering, and morphological analysis were used to attempt to detect only grain boundaries. But as we can see, this was not successful. If we zoom in, we'll notice that yes, many of the grain boundaries have been identified, but also nearly all of the twins have as well. Again, this isn't surprising because the twin boundaries have such a sharp, high contrast that they've been impossible to ignore. Even with the unique combinations of morphological image processing that can be carried out in MIPAR, our team was not able to create a conventional image analysis workflow that effectively identified the grain boundaries as well as our human brains seem to be able to. So, with the addition of deep learning technology to MIPAR, this problem was finally solved. The deep learning trainer allows users to trace features of interest, or they can submit traced images to MIPAR for training. And a deep neural network-based model is then built, which learns to recognize the features of interest simply by how the users have traced them. So our team took a manual grain tracing of these grains as training data and trained a deep learning model on it. And the results blew us away. So what you'll now see is the current state of the art deep learning based recipe applied to this image for automated grain detection. Let's clear this out and load in the new recipe. So, this recipe does a few extra things. The first, of course, is an accurate grain boundary detection while ignoring the twins. We'll notice it also partitions the grains into ones that touch the edge and ones that don't. And we also have the convenient ability to make a few manual edits to this segmentation if necessary. This result was produced purely automatically with no manual intervention. And while it does a remarkably good job, there may still occasionally be instances where a few corrections need to be made. We believe in not only facilitating automation as much as possible, but still leaving the opportunity for the user to make small corrections, especially when those corrections can have a large impact on accurate measurements. So for example, this particular boundary up here probably should be removed. So to do so, we can edit the Edit Boundary step, and we can use our pen tool and simply cross out boundaries we do not want. Click Accept, and that entire boundary is removed. Similarly, missed grain boundaries can be added in. Something like this is a boundary that should have been identified. So again, we can go into our editing step, and with the pen and fill mode, just roughly draw a line where the boundary should be. Click Accept, and MIPAR will clean it up for you and add the boundary. Now, especially with deep learning, if you find yourself making numerous corrections on several images, well, those corrected images can then be used to retrain the model and improve the results. So this really allows for a continually improving model that becomes more effective and more robust the more that you use it. Again, without any more experience required than how to trace features. So this deep learning based recipe was a remarkable breakthrough, and we've seen very excited adoption by many researchers who had struggled with automated grain analysis in heavily twinned materials. Now, of course, rarely do folks stop at segmentation. Segmentation, or accurate feature detection, is key for accurate quantification, but usually the quantification is the end desired result. MIPAR offers many different measurements that can be extracted from image segmentations. They include measurements known as global measurements, which are single measurements per image. They include feature measurements, which can be made on a per feature basis and then averaged together, or other statistics of those feature measurements like minimum, maximum, standard deviation can be extracted. And we even offer local measurements, or per pixel measurements. For example, local feature thickness or local volume fraction across an entire field. In the case of grain analysis, ASTM E112 grain size is a popular measurement. MIPAR offers several ways to perform this measurement compliant with that standard. The one I'll demonstrate today involves a per grain diameter measurement. Those diameter measurements can then be averaged together, and the average diameter can easily be converted to a unitless ASTM number if desired. Measurements can easily be added to the recipe at any time by the user. In this case, this recipe already has the necessary measurement step added, so all we need to do is select it and push play. What we see now is a grain by grain color coding of diameter measurements, as well as a color-coded corresponding histogram on the right. All of this data is linked together, so when any particular cell is selected, that feature is highlighted. This can be a very useful way to explore your quantification visually. It works the other direction, so click on a feature, and that particular cell is highlighted. And you can even choose to drop a line on the histogram where that feature sits. All of this can be further customized, of course, with a change in color scale, a change to your color limits, formatting changes, additional bins in the histogram, and so on. And all of those customizations can then be saved right back into that recipe step. So the next time you or one of your users runs the recipe, they can produce the customized measurements with a single click. All of this can be exported both the individual graphics and underlying data, as well as full formal reports. So that's great for a single image, but of course one of the big questions is, how well does this solution work on other images? Well, let's take a look. To apply this recipe to another image, we can simply drag it in and choose Reload. So here we see another effective grain segmentation where the twins have been ignored. The measurements appear automatically, or the summary statistics of the measurements appear automatically. This could be populated with the additional stats, min, max, and standard deviation, if desired. And measurements can, of course, be applied to the multiple layers in the image. If there were measurements that wanted to be made on all of the grains, not just the complete ones, then measurements could be added to that layer as well. We may want to add a quick correction here. And then take a look at our measurements. Let's take a look at another image, drag it in. And despite the significant contrast difference of these features, we still see a remarkably accurate grain detection. And another one. Different imaging conditions still, and quite a good detection. Even a feature like this, that has twins at multiple angles occupying half the grain. The deep learning has done a remarkable job with very few training images at learning how to detect these features. So, you've seen several images processed one at a time. Now this process was quite easy, dragging in and clicking Reload. But when users have typically more than 5 images, they enjoy the batch processing functionality of MIPAR. So, if we wanted to, say, calculate the mean grain size automatically across all 4 of those images, we would use the batch processor. We'd open it up, choose our recipe, drag our images, and say process. Now, because we have measurements added to this recipe, in addition to the processed images, we will have a batch measurement report waiting for us in the output directory. But we can also produce those measurements from our batch review environment, known as the post processor. When the batch is finished, click View Results, and this will automatically load the batch results in. We can flip through each image to see how the detection performed. If needed, we can make manual corrections in this environment and save them. And once we are ready to perform our measurements, we can do that down here. We have both global measurements as well as feature measurements available. So if we wanted to take a look at the mean grain size across all images, we would do so by clicking Measure Features, choosing off the desired measurement, choosing the desired stats to report, and say Add to Report. We then click Generate. We want to make these measurements on the complete grains, and we'll then get our measurements like this. If, in this case, these were all fields collected from the same sample, and we wanted to group all of the individual grain sizes together into one overall distribution, we can do that as well. We typically see this when folks used to think they had to stitch their fields together to cover enough area, but with MIPAR's batch processing, we can batch process the fields individually and combine all of the statistics at the end. So to take a look at that, we would say measure features. We'll use this same measurement, and we'll say view measurements. Again, we'll make those from the complete grains. So now we see all grains in all images measured. And to produce our histogram, we just click anywhere in the desired column. Here now we see a histogram of overall grain size collected from all 4 fields grouped together. So in this example, we saw the successful automation of an incredibly challenging problem, accurately detecting parent grain boundaries while ignoring the many twins inside. This enabled the desired measurements, in this case, mean grain size, and our users are now able to perform this critical analysis with traditional SEM imaging over EBSD, which offers orders of magnitude in cost savings. So, let's take a look at our next case. In this application, we look at quantifying particle size in an extremely challenging condition. In this case, as mentioned in the introduction, we see a number of challenges. The first involves particles sitting on top of one another. In some cases, these are legitimate satellite particles. In other cases, they're simply static adhered and are not actually chemically bonded, but nonetheless, they still need to be accurately identified as separate from what they're sitting on top of in order to get an accurate size distribution. In fact, many researchers have looked to switch from traditional laser-based approaches to size measurement of powder particles because of the concern with agglomeration, where particles that are stuck together are seen as one complete unit rather than the size of the individual particles being accurately measured. So that's the first challenge, overcoming features that sit on top of other features. And like I've mentioned, this challenge is not unique to this particular problem, and MIPAR has helped address challenges like this in many other applications as well. The second is the rather strict conditions that were placed on what are treated as separate features. In a case like this particular user wanted this entire cluster treated as one, where if you move to something like this, the slightly darker, locally darker boundary between these two features means that they should be separated. And for those of you who have experimented with traditional image analysis approaches, that can be often very difficult to accommodate. Using separation tools like Watershed will often separate features like this as often as it will separate ones like this. The third challenge then involves the contrast variation of the features. In many cases, the particles are brighter than the background, but towards the edges of features, the contrast tends to die off, and you end up with shadows that cause the particle gray value to be, in some cases, darker than areas of the background. So in order for accurate size or shape measurements to be possible, the particle boundaries need to be just as accurately detected. In other words, as many of you are aware, measurements are only as good as the feature detection. So let's move back into MIPAR and take a look at this solution. With the image opened up, we'll load the recipe. What we'll first see are a few different layers. The objects in red are ones that are sufficiently unobscured for us to accurately and confidently measure shape attributes, such as roughness. In the case of the yellow ones, the nature of how they're obscured by other features would produce artificial, inaccurate shape measurements. For example, something like roughness, which surrounds the feature with a smooth hull and then compares the area of that feature to the area of that hull, features like this, which are obscured by features sitting on top of them, would have an artificially high roughness. So we're going to ignore those from shape measurement. Everything now in yellow, though, are features that are perfectly suitable for size analysis. So when we take a look at some of the steps which are conveniently exposed to the user for adjustment, we kind of get a feeling for how the algorithm is constructed. The brightness marking first is an attempt to identify portions of particles that are obviously particles, but then allow for that marking to grow and snap to the particle edges to overcome the contrast dimming towards some of the edges due to shadows that I mentioned before. The separation darkness allows us to control locally how dark particle separation areas need to be in order to trigger a cut. And then the separation completion strength is another knob which allows us to control how strong the final feature separation is. And tuning these settings has allowed us to build a sophisticated algorithm that can meet the criteria of this application, where, as I mentioned, features that you might think should be separated should be treated as one unit, and it's only when significant shadowing is observed at particle boundaries, such as this, that features should be cut. And this allows me to mention a very key component of MIPAR solutions in that they are almost always customized. We don't view customization as an afterthought. In fact, most of the solutions that our users build for themselves, or ones that we help them build, are built for their particular problems to address their particular challenges. The nature of MIPAR's recipe building environment, especially with the deep learning technology, allows our team and our users to effectively and quickly put together custom-built solutions that really work for them. Now, this last step here is a similar manual edit step that we saw with the grain examples, where if there are features that need manual adjustment, such as particles that were not cut that shouldn't have been, that can be accomplished just as we saw with the grains. And when we take a close look here, we notice that there are many particles, small ones, that sit on top of others that have been pulled out. And as we mentioned in the beginning, this is a critical component of accurate size analysis. Separating the clusters into their individual constituents allows us to get a full picture of the particle size distribution and not ignore ones that sit on top of other ones simply because they're hard to find. Now, you'll likely notice that there are some small satellites that have not been pulled apart. This is still a marked improvement from more traditional solutions where particles like this or like this or this would often be ignored in their size measurement. But as mentioned with the grains, with the advent of deep learning technology, you can make your manual adjustments and then, in this example, train a second generation recipe based on those adjustments that only becomes more robust as often as you use it. I'll be clear that this particular solution was put together without deep learning. If required, a deep learning component can be added if needed to meet your project requirements and your level of required robustness. So with many challenges overcome, accurate particle separation, picking up on tiny features that sit on top of other ones, and accurately delineating particles right to their edge despite low contrast, we can now confidently extract our measurements. Let's take a look at particle size. Here we will click on the feature measurements of complete particles, which will measure every particle here in yellow. We click play, and just as before, we are greeted with a size distribution. Each particle is colored according to its, in this case, caliper diameter, or the longest length that spans the feature. And again, we see a corresponding color-coded histogram with summary statistics here. Now let's take a look at some shape measurements. So if we come over here and choose to measure the shaped particles, in this case the red ones, we'll see a few different shape measurements that have been preset. Roughness, as I mentioned, is a metric of feature abstractness, where a smooth circular feature would have a roughness towards the minimum of 1, and a more abstract concave feature would have a higher roughness. Eccentricity is a measure of elongation, where a circle would have a minimum of 0 and a perfectly straight line a maximum of 1, sort of a normalized aspect ratio. And in both cases, the color coding is quite useful to fully interpret and understand the meaning of these measurements, in addition to making great graphics to share with others. So there we have accurate size and shape analysis of particles in a challenging case, permitted by accurate segmentation, which overcame those challenges. This, of course, was made to be repeatable and batchable. To take a look, we can drag in another example and choose to reload the recipe. Here is another image from the same powder lot, and we see its accurate detection. And here is an even more challenging case where there are many particles sitting on top of others. But the solution prevailed and accurately delineated features according to the project requirements. As you saw with the grains example, of course, these fields can be batch processed with all measurements generated at one time. So previously, these researchers had to rely on either inaccurate automation with other tools, where particles were separated inaccurately, small satellites were ignored, and/or boundaries were drawn imprecisely, or they had to resort to manual tracing exclusively, which of course is quite tedious, subjective, and costly. With these challenges accommodated, with MIPAR's solution, they were able to graduate to an accurate, high-throughput automated solution. So now, let's take a look at our final case. The incredibly challenging nanofiber thickness quantification. Here we see an SCM image of a chaotic and heavily overlapped nanofiber network. Often the aim of images like this is to quantify the thickness distribution of all visible nanofibers? Well, there are two main challenges. Primarily, gray values inside of the fibers are quite similar, if not identical, to ones in the background. Certainly deeper down in some of the voids, the contrast is better, but in areas up higher in the depth of field, we end up with background intensity that is just as bright, if not brighter, than the fibers. And secondly, the overlapping nature of the fibers makes it next to impossible to discretize each individual fiber, if such a thing is conceptually even feasible, in order to get fiber by fiber thickness. So we need to overcome both of those. The first is a segmentation challenge, the second is a measurement challenge. Now, prior to an automated solution, this research team had resorted to drawing a few line measurements on these images where they felt they could measure the thickness. And of course, not only is that very time-consuming, as we all know, but the variability is off the charts. Not to mention the fact that the measurements aren't particularly useful to visualize. There's no ability to visualize fiber thickness on something like a color scale when you're just drawing some random lines. So here was another case in which our deep learning technology proved critical. Again, as we saw with the grain case, with a bit of input tracing from the users, we were able to train a deep learning model to do what our brains seem to do so well, which is to recognize the fibers completely separately from the background. And over on the right here, we see an example of that detection. This complex network is accurately detected as the object of interest, where the background, despite the sometimes identical gray intensity, is ignored. And this finally allows for automated, accurate nanofiber thickness distributions in a matter of seconds. So let's move into the live demo. Let's first take a look at what a conventional solution would give you. This is one that is largely based on intensity thresholding, and as we expect, will not do such a great job at distinguishing the fiber network from the complex background. So here we see not only quite a bit of noise in the overall fiber selection, but in areas of heavy fiber crossover, and there are quite a few, this algorithm is completely incapable of accurately delineating the fibers. And this is especially apparent if the opacity is increased to the point where we're just looking at the fiber selection. Certainly one would not expect to get any sort of accurate fiber thickness measurements from a segmentation like this. So, as mentioned in the introduction of this application, a deep learning model was trained to recognize this complex network separately from the background, and a recipe using that deep learning model was created. So let's clear this one out and take a look at the deep learning based solution. So there we see a much more accurate fiber detection, reliably avoiding not only background areas, but fibers that are far too low in the depth of field to get accurate thickness measurements on. Even areas like this, where the fibers are sitting on top of a very bright background portion, a background that in many cases is much brighter than other fibers elsewhere, the deep learning model successfully recognizes those individual fibers. Now, of course, armed with an accurate feature detection, we can extract some very useful measurements. In this application, we will look at local measurements, ones that are made on a per pixel basis. So we'll go into our Measure Local tool to get started. We'll switch the measurement to thickness, and what we'll now do is use our smooth approach to extracting the center line. Center line extraction is a requisite for thickness measurements like this. What this will do is it will aim to draw a skeleton along the fiber network such that at each point on this green skeleton, a circle will be fit to the surrounding features, and we will then use the size of that circle along this entire centerline network to extract local thickness measurements. So we hit generate, and the measurements are made, in this case in nanometers. And if we pick any cell in this column, we visualize our thickness variation. Now we can go ahead and change the color map and adjust our binning to something more appropriate. And here we now see a nice thickness histogram showing that we have an average fiber thickness of 30 nanometers, a minimum of 10, and a maximum of just over 100. And this histogram and its statistics nicely complement the color-coded thickness visualization, where we can verify that in fact the thicker measurements that are coming from the sample correspond to actually thicker portions of the network. As we mentioned before, all of this can be exported, either the individual components or a formal report to share. So here we saw another breakthrough application of deep learning technology, which has finally allowed computer software to catch up to the human brain and extract incredibly challenging features that permit automated measurements. Today we've taken a look at 3 cases. Each case highlighted key challenges that are not only seen in their respective applications, but across many other applications in many other fields of study, including life science, agriculture, food science, even satellite image analysis. So I wanted to conclude this webinar with a discussion on the various types of users that we encounter. If you are a user or researcher who is really just after the results of image analysis, but doesn't have much experience in the field, you'll find that MIPAR offers a friendly environment in which you can run the analysis algorithms, either provided by our team or downloaded from our website. As you saw during today's demos, simple drag and drop is all that's required to execute these powerful solutions. As I've mentioned, these solutions are almost always custom built to your particular problems and your particular challenges. And if needed, our team and our online help material can train your team in software operation and consult as projects grow and evolve. If you have an interest in becoming more experienced in image analysis algorithm building, we encourage you to check out our MIPAR Academy, which is a self-paced Udemy course, completely free, that will walk you through the fundamentals of image analysis and how those can be applied in an environment like MIPAR to address real-world image analysis problems. As I've mentioned, there's absolutely no coding involved in any of the algorithm creation in MIPAR. It is a purely graphical, interactive algorithm building environment, and that toolbox combined with a resource like the MIPAR Academy has been shown to be incredibly educational in raising the experience level of our users. We do have our recipe store available on our website that offers many pre-built solutions. These tend to be treated as learning material where you can download the recipe and example images and learn from how they're structured, with the understanding that they can easily be tweaked either by yourself or by our team to accommodate your particular problems. On the image analysis expert side, the toolbox is an incredibly effective algorithm builder, again, very visual, very interactive, allows experts to perform a vast number of what-if scenarios in their quest for an effective algorithm, and we found that seasoned image analysts reach a level of creativity and solve problems that just weren't practical with hard-coding tools. As you've seen, the measurements that you add to the recipe are immediately generated upon execution, and that allows your experts to configure the entire workflow to be run with a single drag and drop by perhaps less experienced operators. And lastly, I'll mention that we do offer an API that allows your apps to execute MIPAR recipes with a single line of code if you are looking for that level of integration. So thank you very much for your attention. My name is John Sosa, and I'm the CEO here at MIPAR Image Analysis Software, and I and the rest of our team very much look forward to working with you on your image analysis problems.